Okay, so that's kind of a comprehensive skeleton outline of material for Exam 1. Okay, so if you've got specifics, send me an email. I've set up a Zoom chat with some of you guys. I don't mind doing that. If that's more efficient, if you're more comfortable with that, we'll find a way to communicate and try to get your questions answered. But that's my hope. What I often find is if you've seen the theory once, kind of in a regular lecture, you've worked some problems now, you've kind of tried to put it to practice like engineers do, take new knowledge, put it to practice. So you try to solve some problems. And now if you come back and look at the theory again, kind of in a slightly different format with more knowledge on board now, it tends to click a little more. And that's kind of the hope there. That's the reason I do just kind of a skeleton outline for review. And we can talk a little bit about logistics of the exams. Like I say, on Monday I'll post some information about how the exam's going to work. So, where does that leave us then? That leaves us with the rest of Chapter 3 to talk about before we try to move on to Chapter 4 after the exam. So let's do that. So the rest of Chapter 3, got to pop here. I want to make sure I don't have glare on the screen. Okay. So the rest of Chapter 3 in your text is going to talk about the concept of what we call equations of state. Now, as we mentioned, historically what we've done a lot of times is we'll publish tables. Instead of giving you an equation, we don't give you an equation for a U value or equation of how P, V, and T relate to each other for water in R134. We just say, no, here's property tables, here's how you use them. That works really good, but there are some substances that behave so predictably that we can actually put them into a pretty simple equation that's pretty easy to work with. And that's what's called an equation of state. So, can you think of any can you think of any substance or a group of substances where I would have an equation that relates pressure, temperature, and volume of the substance to each other? Can you think of any laws, expressions, or equations that do that? Well, you've had chemistry before, and my assumption is they've talked to you about ideal gases. I think that's Boyle's law, right? The idea that, and by the way, no gas behaves ideally, but most gases behave pretty close to this principle of the ideal gas law. Now, what you've probably seen in your chemistry class is something like this, where we would say, well, P times V is equal to N times, I'm going to say R sub U. Right? That's R sub U. It's not R times U. It's R sub U. This R sub U is the universal gas constant. Now again, this material doesn't show up on Exam 1, but it does show up throughout the rest of the course. So there will be times we will encounter things that are in the gaseous phase, and ideal gas is a reasonable assumption for those. Now, this form, we will not use this form. You can. You're welcome to. I won't, because we tend to use what I call the thermo style of ideal gas law. And that's where we say, well, remember there is also this form where in chemistry, how do you find the number of moles? Well, you take the mass of your sample divided by the molar or molecular mass. Right? So that's capital M is the molar mass, if you will. Right? And what we normally do with that is say, well, what if we just do this? So what I did there is I said, well, R is the universal gas constant divided by the molar mass for the particular substance, and this, we just call this the gas constant. Right? It is specific to a particular substance because this molar mass is going to be different for different substances. one reason we do this is rather than trying to remember the molar mass for air or nitrogen gas or any other substance into a reasonable number of significant figures, we just say, well, you can just go look these up in table A1. Table A1 will give you these values. That's the first table in your appendices. You'll become more and more familiar with those. So this is the form we'll use. Nothing wrong with any of them. But this one's also pretty handy. If I don't know the mass, that's fine, just divide by it. So take the specific volume, the reciprocal of density. P little v is equal to RT for any ideal gas. Okay? And this becomes very, very powerful. And you probably saw this in the chemistry class, right? Remember, if I've got more than one state, so let's say I've got P1 V1 divided by T1 is equal to R is equal to P2 V2 divided by T2. Or later on, like when we get to chapter 9, we'll actually have 4 different states we'll deal with, and we can set this up. What I like to do with the ideal gas law, if I'm going between multiple states, I like to put everything that's constant, put that in the middle, and set everything equal to that. Right? And then you can kind of see how to build the equations from there. Okay, so, and again, like I say, later on we'll actually deal with 4 different states. But the R is always constant, and maybe something else is constant between all 4 states. Maybe the mass is constant, or whatever the case may be. Okay, so if I can put the constant values in one side of the equation, the variables on the other, then I can set that constant equal to the variables of all states. Okay, so very powerful, very simple, easy to use expression there. You do have to use absolute T's and absolute P's. You have to use absolute temperatures and absolute pressures. Right? Okay, where do we go from there? That's a good question. Can you use ideal gas law? Well, I hope they talk to you in a chemistry class about the idea that no gas is ideal. It is only an estimate. It's a pretty good estimate, but it's only an estimate. Okay. How do we know if we can use it? Well, sure. If I know I'm in the gas region. Right? Where is the gas region? Well, that's if my density is low or my specific volume is high. If my pressure is low, then okay. What's low pressure? Well, where are you in relation to the critical point is kind of the best thing, and that depends on the substance. So it's low and high are relative terms, right? So how do you know if you can use the ideal gas law? Well, I'll be honest with you. If it's water in R134, I'm just not going to use it unless the problem tells me I have to. I'm not going to use for water R134 ideal gas law because I've got perfectly good superheated tables if I'm in that gaseous region that are going to be much more precise than the estimate that is ideal gas law. But if I'm dealing with something like air, the air that we're breathing, or carbon dioxide or carbon monoxide, or something like that, then something I know is going to be in the gaseous space for most practical purposes, sure, I could probably use the ideal gas law, and that'll get along just fine. Okay. Now, how do we know? Well, this graphic is in your text, right? So this is from the Changel and Bowles text, and what this represents, these numbers here are representing the error associated with using the ideal gas law. So what they're saying is, at this pressure, so let's say at 100 kilopascals, this pressure, that's about 1 atmosphere, right? If I took water vapor at 100 degrees C and 100 kilopascals right here at the saturated vapor point, if I took actual water vapor and measured its specific volume, which is what the property tables for the most part do, If I took that value and compared it to what I would get from the ideal gas law, if I substituted in 100 kilopascals, 100 degrees C, and solve for V, if I take this value and compare it to actual water, saturated water vapor, I would get about a 1.6% error compared to the ideal gas law. But if it's a lower pressure, if it's down here at like 10 kilopascals, a tenth of an atmosphere, notice it's even for saturated vapor, it's almost the exact same, whether I'm using property tables of the ideal gas law. So they've highlighted this region here, right? So again, lower pressure, the lower the pressure, as you increase the pressure, you see these numbers start getting higher. As you increase the temperature, they do get a little further away, but as you get closer to this critical point, as the pressures get closer to this critical point, notice the errors get pretty out of hand. I mean, up here, 271% error, over 100% error for 20 megapascals. I think the critical point for water is like 22 megapascals. So can I use the ideal gas law? Well, yes, but we have to understand it's only an estimate and it has its limitations. I have to understand if I get close to the saturation dome, especially if my pressure increases, I'm going to notice an error. Okay? And the petroleum engineers that I talk to that are out in the industry, they say, they'll tell me, look, ideal gas law doesn't work for us. We're dealing with typically we're dealing with pressurized substances at high pressures, approaching the point of liquefaction, or if we get it to a liquid, then it's easier to ship. Right? So we don't want it expanded out. It's at low density and low pressure. They need it at high pressure, low density, or high density, right? Low specific volume. So it's you just have to be aware that ideal gas law for us in a textbook might be an okay estimate, but when you actually get out in the field, nothing behaves ideally. So can we use it? Yes, if you have air. For our purposes in this course, unless the problem statement tells you to use another method, I'll be fine with using ideal gas law for air, for nitrogen, for oxygen, for those substances. Don't use it R134, period. Unless, the only reason you'd use it for R134 is if you knew it was going to be in the superheated vapor region at all states. And we use R134 because it liquefies or goes through the saturation process at favorable temperature pressures for us. So it's a good chance that water in R134, we're going to deal with at points where they're too close to the saturation dome, the air is too high, so don't use ideal gas for those substances. But for air, carbon dioxide, carbon monoxide, sure, go for it. And as I mentioned, the closer you get to the critical point pressure, the higher the error associated with ideal gas law is. Okay? Okay, there are various ways that we can improve the ideal gas law. There are various things we can do to improve the ideal gas law. There is what we call the generalized, compressibility factor. Right, so this is the Z value, if you will, capital Z value, the generalized compressibility factor. Okay. Now let's talk about what that Z value is. So you have this. It can account for some of the error associated with the ideal gas. So you can find this chart graph in your text, and this should be, if you're using a different text, you should be able to find something like this. What they've done here is they said, look, we did all these tests with all these different substances, plotted them on charts using what they call the reduced pressure and the reduced temperature. Right? So they've got a reduced, it's not actual pressure, it's reduced pressure and reduced temperature. We'll talk about those in just a second. What they're saying is to put them all on the same curve, the same chart, and compare. Notice, and we plot all these data points, patterns emerge. That's what we'll pick up on the next video.